he'll be defending. So the jokes can start now. All right, so today Jarrett Lardy is going to be providing a seminar overview of his research that he's been doing the last couple of years. He was born and raised here in West Fargo, over there in West Fargo, right? And then so his family on both sides has deep agricultural roots in North Dakota. Both sides of the family ranching and farming. Early on, he had close ties to NDSU, having worked numerous summer jobs for groups in Experiment Station, the Greenhouse, Plant Path, Range Science, in which he earned his bachelor's degree at NDSU in Range Science, and now is working towards his master's in soil science, where he is co-advised by myself and Dr. Miranda Meehan. His interest in Western North Dakota began at a young age, having spent many hunting trips near the Sentinel Butte area, where some of his family originates from. And from there, he has worked on a ranch near Grassy Butte, followed by internships with KLJ Engineering, and then which helped him gain an interest in the oil and gas industry. And so, one of the things that you have to give Jarrett a lot of credit is that when he started, it was right during the pandemic, so nobody was here, and so he was sort of like in this no man's land of a graduate student between working at home, trying to figure out what he needs to do, and also understanding that he has responsibilities here. And so probably the greatest, I would say, advancement in a young man was probably Jarrett, because of the fact that he had to start with basically no one here. And so today he's going to give us an overview of his research. Once he finishes all this nonsense, then he does have a job with the NRCS in Detroit Lakes, Rock City, Minnesota. And so some of you will catch the reference. One of the things that I get these calendars, these daily calendars that help me sort of figure out tricks to appear smart in meetings. And so today's actually happens to be get someone else to control your slides. This puts you in a position of power where you can say things like, next slide, please. Just go back a few slides. And please try to keep up with me, Tom. So with that, Jarrett, I'm going to leave you the floor. And again, there's coffee and donuts in the back. So we'll give Jarrett about the next 90 to 120 minutes.
Right. Well, thank you for that, Tom. I'll share my screen here. Well, thank you everyone for being here for my research seminar. I'll be presenting some of my master's work that I've been working on for the last 2 years. My talk is titled An Examination of Lamb Preparation Methods. For pipeline restoration here in North Dakota. And we'll be talking about some of the common issues that they have. So this work is organized into 3 different chapters. The first one being an overview of the oil and gas industry here in the United States, but then also here in North Dakota. There we'll discuss some of the challenges associated specifically with pipeline reclamation and installation. And then we'll talk about some common reclamation practices that are used to restore some of these right-of-ways. And then in chapter 2, we take some of those methods and apply them in a field study at the Wilson Research Extension Center, where we examined several methods for things like runoff, erosion, and then plant establishment. And then lastly, we'll wrap it up with chapter 3, which is a laboratory study where we examine how penetration resistance is influenced by varying water content and bulk densities. And then we'll have time for questions at the end. So to start off, here in the US, nearly 69% of energy consumption stems from things like oil and natural gas. A big part of why this is due to the cost of these commodities, but then also their availability. As a result, production in many states has ramped up, and we know that very well here in North Dakota, as production is now at a record high. In the next few slides, I'll kind of build you a picture of how production has since surpassed transportation and why that has become a problem in some cases. So here in North Dakota, oil production specifically has increased since about 2006. A lot of why that is because of new technologies such as hydraulic fracturing and horizontal drilling, allowing oil to be much more accessible from the Bakken and Three Forks formations in the western part of our state. As a result, North Dakota became the second largest domestic oil producing state in the Union, only behind Texas, and we've remained there since about 2012. And then North Dakota set production high annual production of crude oil at 524 million barrels of oil in 2019. As a way to capture all this product, there has to be a lot of infrastructure constructed in the western part of the state. A good indicator of that is the amount of well pads in the western part, focusing around the Bakken and Three Forks formations. As you get closer to the center, the density of those dots, which is about 20 square miles, increases to about 60 wellheads per 20 square miles, which is rather impressive because there's nearly 17,000 wellheads in the state. And since that 2006 benchmark, that's an increase of nearly 14,000 wellheads. But in order to support all these, there's a lot of pipelines. However, a big reason of why pipelines need to exist for natural gas specifically is due to this flaring that's occurring. Historically, about 30% of the state's natural gas was flared off, and that's mainly because that that production was exceeding transportation. The North Dakota Industrial Commission, you can see that that rate drops off, imposed some goals for capture of natural gas beginning in 2014 at 75%. And whenever that light blue line is below the dark blue line, that means that goal is being exceeded. And so I'm happy to report that as of the third quarter of 2020, most recently, there was over 92% of natural gas captured in the state. There's a lot of pipelines in the state for natural gas, and here in North Dakota, there are also 25 different natural gas refineries, and those pipelines connect the refineries to the wellheads as a way to transport them and become a commodity in that way. But then also there's numerous oil pipelines in the state, and when you combine oil and natural gas, there's nearly 30,000 miles of pipeline just in North Dakota. A big reason of why this is challenging is because of how these pipelines are constructed. Initially, soil is stripped and stockpiled and separated into topsoil and subsoil, and I'll show an image in a bit. And these right-of-ways are often 50 to 125 feet wide. They are typically about 3 feet in depth, and you can kind of see the scale of just how destructive this process is. Here in North Dakota, since there's about 30,000 miles of pipeline, at a typical width of 75 feet, you're looking at least 400 square miles of disturbance, and that's about the size of 4 national or Theodore Roosevelt national parks. These pipelines impose a number of challenges to the reclamation process. The biggest one in some cases being compaction, and this is arising because of heavy machinery use on the right-of-way. These right-of-ways often have decreased porosity and thus lowered available water for plants to then take up. And the native grass or cropped plants that are reseeded on some of these right-of-ways often struggle due to that compaction when that water is lowered, but also because roots cannot move through some compacted layers. As a result, invasive species often move in. These are typically annual plants which have finer roots and are able to establish on shallower topsoil depths. But then also another common issue is the topsoil and subsoil mixing. Initially in a right-of-way, you maybe had a foot of topsoil, but then during that soil respreading process, once the subsoil is spread about the right-of-way, after construction is complete, followed by the topsoil, you may see a depleted topsoil layer, which initially was a foot, and you maybe have several inches. This leads to also decreases in plant productivity, which result in lower establishment altogether. And this then increases erosion along the right of way. Plants are crucial to keeping soil where the right of way is, and this creates a problem for companies as they then have to reseed their right of ways multiple times, which ends up costing companies money, which is what they're concerned about. But in our case, we're more concerned about the time since restoration. Time's an incredibly crucial portion to this, as the amount of time goes on, and especially with erosion, you may be losing topsoil and thus hindering your chance of success in the long run. This rolls us into our chapter 2, where we took several methods that are common in the oil and gas industry and applied them at the Wilson Research Center. We wanted to know if there was a seed prep method which would benefit pipeline restoration in the long run for runoff and also erosion. We also want to know if any of these methods were able to increase plant establishment, which is one of the main pillars to reclamation. For our study design, we built 3 different blocks in a strip plot design at the WREC. The WREC is in a semi-arid region, which typically receives about 13 inches of rain. And I understand they have nearly a third of that at the moment, probably more. But in 2020, many of us know we were experiencing a severe drought. And so in 2020, Wilson received about 4.5 inches of rain. And then in 2021, the drought continued, where Wilson received about 7.5. For the study site, we had 2 different soil units. Along the tops of our blocks, we had a William Bowbell complex, and then closer to the bottom, we had a Vita Zolhill complex. And that Vita Zolhill complex saw slopes of about 2 to 8%. And this allowed us to measure different slopes in our study because of that strip plot design. Along the tops of these blocks were 2% slopes, and then along the bottoms were 5% slopes. For treatment uniformity, we broadcast seeded things like oats at 10 pounds per acre to get some establishment over winter, but then also a native seedgrass mix, which is commonly used in right-of-ways when contracts may not specify a certain seed mix. And that seed mix included side oats grama, green needle grass, slender wheatgrass, and western wheatgrass. For our treatments that we applied, the first one is straw crimping. You can see that it costs about $1,400 an acre. Straw crimping is a great method at controlling erosion as it provides cover and allows water to infiltrate down into the profile. The reason that water is able to move downward is because of the implement on the bottom right, which forces the straw into the profile and pins it vertically, allowing the water to move downward rather than across the landscape left and right. Straw crimping also provides some carbon for the right-of-way, which is important to limiting potential invasive plants, as those need a high carbon to nitrogen ratio. The next method that we tested at the WRC was land imprinting. Land imprinting uses these microclimates that you can see on the left side and right side of these pictures. And they funnel seed, sediment, plant material, and water downward as a way to improve plant germination for these right-of-ways. The idea is that this also can break up crusting in certain environments, and Dixon et al. Was commonly cited as using it in arid environments to do so. Here's a closer look at what the land imprinter looks like. On the left side, this land imprinter in particular that we use leaves about 50,000 of those impressions on the landscape per acre. And then you can see on the right that those imprints are roughly 3.5 to 4 inches deep. The third method that we tested is the use of hydromulch. Hydromulch is the most expensive of the 3 at $6,400 an acre. Part of that reason is because of the need for water within this treatment. This is particularly difficult in some right-of-ways, depending on their slopes and accessibility, as you need to have a water source nearby or a water tank like so, and those can be difficult in some situations. Hydromulch typically creates a seal on the right-of-way, and that often limits the evapotranspiration that is occurring on these right-of-ways, especially in the hot summer months. This method also lowers the temperature that those right-of-ways see, and that is essential for allowing plants to then germinate. And another reason that this method is usually more successful at creating or increasing plant establishment is because of that initial water source that is provided. Some cases you can incorporate the seed into this water tank and you can spread it across your right-of-way as such. However, as I mentioned before, we broadcast seeded for treatment uniformity. Lastly, we combined imprinting with hydromulch, and that became our most expensive treatment, as you can see. The reason we combine that is because of that seal that the hydromulch creates. It often increases the runoff that is seen in these right-of-ways, and as such, you are losing rainfall in that regard. The idea was that combining it with those imprints, we might be able to capture some of that, if not most of it. And then lastly, we had a bare ground control. You can also see kind of how we were collecting some of our runoff. We used a steel box that was 3 foot by 6 foot, and then the trough system on the bottom to funnel water into our collection devices. For this rain simulation that we applied, we did 2 simulations, and each simulation applied 50 gallons of water at 30 minutes. And this ended up simulating a 1 in 25-year rainfall event. We conducted these simulations in September of 2020 and June of 2021 because these treatments, or because this area often sees the highest amount of rainfall during such time. As a way to analyze our runoff and erosion, we used that trough and bucket method that I described. We had sheet metal keeping the soil face held back, and then a PVC pipe along the bottom to funnel water into the bucket, and several peristaltic pumps to then bring the water and sediment out of the bucket and into a larger collection device to be measured. You can see with the right-hand photo that this was rather labor intensive for our crew. We needed several generators to run the pumps, but then also the rain simulation. And our water tank held about 100 gallons of water. And so we were able to get 2 simulations out of each water tank. And so that truck was moving back and forth to our water source quite often. Back in the laboratory, we used the water collected from the runoff and multiplied it out as an equivalent depth for that runoff plot that I described. And we scaled that up as equivalent depth so that it read in centimeters as one might read rainfall in inches. And then for our sediment load variable, we took 2 samples back to Fargo at 250 milliliters. And then when we got back to the laboratory, we then also took 30 mil subsamples from those and got our sediment load from those. We dried out those samples and calculated how much sediment was within each subsample, and then multiplied that out as a ratio for how much rainfall was accumulated for each plot. Lastly, for plant establishment, this was analyzed in August of 2021 using 1/4 meter Dobemeyer frames, and we ended up grouping everything as one species as plant cover, simply because we had some accidental mowing occur on our plots. This is a table of some of our results. It's a little busy, and so I've blocked off some variables that I won't have time to discuss here today. But I do want to note that within each column, each letter nearby their corresponding number. When letters are similar, they are statistically similar, and when they're different, they're statistically different. One thing to note too is that we analyze these numbers by year separately. So 2020 was analyzed separately from 2021, and that's mainly because of the different climactic data that occurred between 2020 and 2021. First off, we'll talk about the equivalent depth that we observed. Initially, you'll see that there was treatment effects for both years, but then also there was no slope effect for either year. Our 2% and 5% slopes were not making a difference, and that may have been because the difference in slope was just simply not great enough. Perhaps if we increase that difference to 2 and 10%, we might see something fall out. Splitting those two up by year, the first thing that you'll notice is how low that imprint is. That number is fairly close to 0, and we actually did have one trial in 2020 report back 0 runoff. The next thing that you'll notice is how high that mulch is, and that was actually about 6 times higher than our control, and it was statistically different as well. Another thing I like to point out with 2020 is that the combination of imprinting and hydromulch nearly split the imprinting and hydromulch down the middle, and being statistically different than both of them. As time went on, the straw treatment then fell out and was different than the control, being the only one that was statistically different. It ended up reducing that runoff by about 60%. And then the mulch treatments ended up being similar to each other as time went on. Main reason we suspect this occurring is because of the degradation of the mulch, but then also the imprints settling out over time. The Williston Research Extension Center experienced several occasions where wind was in excess of 100 miles an hour, and those imprints aren't designed to be permanent, and so that wind simply just helped them along and degraded them that way. You can see visually how that looked like. Those imprints filled up with water as expected and reduced the runoff, but then in 2021, those plots looked almost identical to our bare treatments, and the results reflect that. Additionally, as we talked about, those mulch treatments shed water. This left-hand photo is a downward facing slope. For our box plots along the sides, we were shedding water so that it would not come into the collection device inappropriately, and this is the water you're seeing. I also think it's pretty cool to see how those imprints fill up with the first one and then spilling into the second and third and so forth downward. The next variable that we'll talk about is the sediment load of that runoff. Similarly to the equivalent depth of that runoff, we had treatment effects, but then also no slope effects. When we split up those treatment effects by year, the first thing that jumps out to me here is that the control and straw treatments are the same. We were hoping that those straw treatments would be different than the control, given that they are allowed to hold that sediment in place, but that did not seem to be the case in 2020. But then also that those mulch treatments really held back that sediment load, cutting it down by over 60% as well. Additionally, in 2021, the straw treatment then was statistically different than the control, making it one of the better methods long-term. But then also those mulch treatments were still able to hold back some of that sediment despite some of their degradation. The third variable that we'll talk about is the lag time to runoff. The results are fairly similar to the equivalent depth of that runoff simply because timing and volume are fairly correlated. I do want to point out that in 2020, we did have a slope difference, and that's mainly because of just how slopes behave naturally. And then our last variable here is our plant cover data. As we noted several times, our sites experienced severe drought, but then also were accidentally mowed, making it a little bit difficult to evaluate this, but none of our treatments ended up being statistically different than each other. And that was also the case for the slopes of these. You can see that even just a little bit of rainfall on that left-hand side photo helps these plants quite a bit. This is in June of 2021 when we were conducting our second simulations. You can see how those plants established where water had previously ran. We did not conduct our simulations on the exact same plots, but you can see that this water tends to follow the same path of least resistance, and that is where these plants established from the year prior. It's interesting that just one 30-minute rainfall event was able to help some of those plants along. Some of our initial conclusions from the study is that the straw is one of the better treatments over time. It had the ability to both reduce runoff and erosion, and not every treatment was able to do that, but also straw is readily available within our state. Here in North Dakota, we're the #1 wheat producer, and that can significantly help some right-of-ways when they're in a pinch for some kind of cover. Imprinting also significantly reduces runoff initially. It was the only one to be near zero in 2020, but those imprints do settle out over time. Additionally, imprinting with hydromulch is typically not different than the mulch treatment. And since it is one of the most expensive methods that we implemented, that makes it our least likely recommendation. And then we can't stress enough how important cover is in times of drought. You need water, as you can see from how those plants were able to establish along the path of least resistance. That water is extremely important to this process. And any kind of method that will conserve water is going to help you in the long run. Leading us into chapter 3, another frequent problem that we had mentioned earlier is compaction. And the reason why this is that when you see a soil profile, the amount of air is greatly reduced in the profile due to those heavy machinery and other factors reducing porosity. And when you look at the pie chart of what a typical soil profile looks like, maybe from your intro to soil class, you see that half of a typical pore is solid material and the other half is water and air. However, when a stress reduces some of that, you often see the ratio decreasing and thus increasing the amount of solids within a given pore. This reduces root growth and infiltration, and thus reduces plant productivity for these right-of-ways. Our initial hypothesis and reason for this study was that compaction is often broadly classified across some soil textures. Say, for a sandy soil, a lot of literature suggests that compaction occurs at 1.7 grams per cubic centimeter. And we want to know kind of if this was the case and how penetration resistance then influences that water and bulk density. Other literature notes that low compaction often restricts germination, and this is because there is low seed to soil contact in that pore. But then more importantly, in soils that have high compactness, these roots have difficulty penetrating the soil and reaching water in some cases. and this leads to reduced water uptake, but then also reductions in nutrient uptake. Somewhat of an inspiration for this study was Ehlers et al., and they used a field setting for their project to analyze the bulk density or to analyze penetration resistance as bulk density influences soil moisture. This project utilized several different plowing techniques, and in their field setting, they're able to identify several different bulk densities. And as you can see from this graph, the penetration resistance tends to decrease as water moisture increases, as that slope is negative. For our research objectives, we wanted to aid the understanding of our reclamation specialists, as they need to know if seeding should occur. And a big part of why that is because they need to know if the water and bulk density of their soils is able to support seed germination. And a big reason that is because penetration resistance that we were analyzing is influenced by both of those factors and is a good indicator of root growth through the profile. This also allows for an assessment of short and long-term goals for reclamation specialists. The penetrometers that a lot of specialists are able to access are readily available and fairly cheap. And they save these companies a lot of time so that they don't have to analyze bulk density samples in a lab and then go back out and determine if seeding could occur. For this study, we brought in 7 different soils from Western North Dakota, ranging in different ECs, pHs, texture, and organic matter. These soils were a little bit limited in that they were both sandy loams, or only sandy loams and loams. They did not have any other textures. These soils were chosen because of their frequency when they're seen on right-of-ways in the western part of the state. For our methods, we saturated our soils to different water contents, and we then placed them in different Ziploc bags, different water contents, and placed them in a refrigerator for 72 hours and allowed them to equilibrate. We then also mixed those soils at 3 different points during those 72 hours to also enhance that equilibration. We also then compacted those soils into this aluminum ring here that you can see, and used a steel plate to transport them between our car jack and our penetrometer. This allowed us to get varying different bulk densities, and that steel plate at the top allowed us to force the soil downward, and we were able to measure the depth of compaction and then determine bulk density that way after the sample was analyzed for their penetration resistance. For our penetrometer, we used a 30-degree cone penetrometer, which is typical amongst many penetrometers that are used. This allowed us to determine the penetration resistance of all those samples with different bulk densities and water contents. For our analysis, we used linear regression for the initial bags that had different water contents. And then as each soil ended up being tested with several different water contents, in this case, we used 6 different water contents. We used stepwise linear regression to analyze those as a way to predict penetration resistance for bulk density and water content. And then finally, we did one final stepwise regression as a way to combine all soils that we had, the 7 different types, and included in that analysis their physical and chemical characteristics that we reported in the previous table. As an example, here's the soil W4. The soil originated from the Williston area and was a loamy soil. Each one of these lines represents a different gravimetric water content from those bags, and we were able to take about 8 to 10 samples from each bag. Along the y-axis, we have penetration resistance from that 30-degree cone penetrometer in megapascals, and then along the x-axis, we have our bulk densities. As these bulk densities increase, we see that the penetration resistance also increases. However, as this gravimetric water content increases, you see the slope of that line decreasing and becoming closer to 0, but it won't ever reach 0, given that there still needs to be a force moving through this soil. One of the reasons that we did this study in this way versus the Ealer study that had them focusing down is that it was a little bit difficult for us to get consistent bulk densities in the laboratory and sampling the same bulk density. And so we chose to sample the same water content for each one. Additionally, a lot of literature, as I noted earlier, denotes compaction happening at that 1.7 mark. And so you can see a lot of these soils aren't actually compacted at all, yet the penetration resistance is quite high. And some other literature denotes that a penetration resistance greater than 2 often restricts root growth. An interesting part of why this is because it might not be that compaction is occurring, but simply the strength of the soil is increasing. Especially at these drier water contents, those soil particles are binding closer together and limiting the availability of a root, or in this case, a penetrometer, to move through the soil, increasing that resistance. Here is the results for those stepwise linear regressions. If you take the W4 example from the previous slide and place it on the second to last line, that is what we came up with as a way to classify the whole soil for both bulk density and water content. When we look at all the different soils for those 7 different stepwise regressions, our R-squared values range from anywhere at 4.9 or 0.49 all the way up to 0.89, which is strongly correlated. And then finally, we did one more stepwise regression analysis in which we included the physical and chemical characteristics that we noted earlier. And we expected some of them to fall out. However, we did not expect something like smectite to fall out. It is also worth noting that 84% of the contribution of each factor's expected or explained variance was influenced by the gravimetric water content and bulk density. Some things to note with this study is that we did talk about the limitations of these soils. This work should be expanded to include more textures, and that this only includes sandy loam soils and loamy soils. Yet we did lay the foundation for a database to be built and expanded upon. In Western North Dakota, there's going to be a need to assess soils pre-reclamation and determine if seeding should occur on these right-of-ways. Lastly, some of those penetration resistances and bulk density limits may shift. You can see that from that W4 example that a lot of those soils did not meet those bulk density requirements for compaction, yet they were still limiting their soils as that strength was highly increased. This also highlights the need to monitor water. Water is the key to this, as we mentioned earlier, and that these reclamation specialists should keep track of what their right of ways are looking like and determine from there if there's even enough water available for germination to occur, as that water will help those roots move through the profile. Some of the overall conclusions for both studies is that we cannot, again, stress enough that there needs to be water conservation for these right-of-ways. A lot of what's going on is that these companies come in and seed several times with little to no success, and then they have to keep inputting more dollars into those right-of-ways on a project that should have been wrapped up a long time ago. We also recommend that seeding should seek out wet cycles in the year. This year would be an excellent example of that, whereas the last 2 years, some companies maybe should have just covered their soils and not even tried seeding, as we had experienced a lot of drought. Lastly, I'd like to thank a number of our sponsors, the big one being One Oak, but then also the North Dakota Water Resource Research Institute. I'd also like to thank the Wilson Research Extension Center for hosting us. And then lastly, the H2 Enterprises for helping us install our plots for those Chapter 2 trials. Here's some works cited. And then lastly, I just want to leave with this. This is a picture of me and my dad. A lot of kids go through a phase where they dream of growing up and being like their dad. I was no different. My dad serves the state in a lot of capacities, and I'm excited for my role with NRCS to be serving the people in that way, and I look forward to somewhat following his steps in that regard. And with that, I'd be happy to take any questions.
All right, do we have any questions for Jarrett? Dr. Hopkins.
So is the straw treatment sort of like air implants? I mean, is the straw just pushed into the ground, or is it bound and inserted?
Right.
How does it work?
So the question for the online folks is, how is that straw treatment being, how is it staying within the ground? Is it like hair implants? And the answer is yes. Those discs force that straw into the ground, and those discs are about 6 inches deep. And so they bring that straw downward, and then the residue that's left on top of the surface stands up and is about 5 to 8 inches tall.
Some companies actually contract people to get a certain length of straw, and so they can get a pinning that is like 6 to 8 inches, on a consistent basis. Questions for Jarrett?
Yes.
Great seminar, Jarrett. What was your favorite part of grad school?
My favorite
Well,
part,
let me stand up here for you.
for the online folks, the question was, what was my favorite part of grad school? There's not a lot I didn't like, actually. Yes, there were tough classes and challenged me quite a bit, but I think what I enjoyed the most is the friendships I made with faculty, but then also students. I met a lot of people from a lot of different backgrounds that I never would have had the chance to meet had I not taken this opportunity. And I'm pretty grateful for that.
Okay. So a question online that maybe Miranda will ask.
Yeah, I'll ask. It's from Lindsay. I'm curious about what production or what portion of the soils over these pipelines in North Dakota are loam, sand, de-loams. Anyway, in other words, are your results relevant to the majority of the soils in question?
So the question was, what percentage of right-of-ways are sandy loams and loams? And I don't know the answer to that, but if you could drop your email, I'd be happy to look into that. I think a lot of what The majority is those textures, because those are the dominant soil series that are being disturbed, and that is what we brought in.
Do you agree, Jim? Kind of in that area, or?
Yes, at least around the medium Williston area.
And a lot of those soils we looked at were from that Wilson area. We had 2 from the REC, another 2 from the Gregor Wilson area, 1 from Arnegard, 1 from Tioga, and then 1 from Dickinson.
And if you would have brought soil back from last week from Watford City, that would have been.
Yep.
Fall right in there.
That'd be a great one to have.
Another question.
How long can seeding be delayed due to drought, and what should be done specifically to protect the soils in the meantime? Just thinking of multiple drought years.
That's a great question. The question was, how long should seeding be deferred? And that's something that I kind of think should be looked at in future studies that Tom and I have talked about in other conversations. It'd be interesting to know how long those seeds are able to be dormant, and maybe you should throw something out there that's an annual, such as oats, like we did in this case, just to get cover established. Because in a lot of cases, any cover is better than no cover. That bare ground is going to be continuously eroded without any type of cover, whether it's from plants or something like straw or hydromulch.
Any other questions? Dr. Hopkins?
I was wondering where you found the bulk density figure of 1.7 for root inhibition. Typically, I guess, radian oil, for instance, and then others suggest it's 1.6
Okay.
for root inhibition. And I was just wondering.
That was our shot at all, 1999 or 96. I can share that with you at a later time. They also suggested that sandy soils are limited at 1.75, which makes sense given the size of the particle.
So kind of a follow-up on that, what we were gonna do, what we didn't have time for, was to actually then have plant germination on each of the cores that he prepared theoretically, and then we could actually get at some of those answers. So, if anybody's looking for something to do. Any other questions? If not, Jarrett, thank you very much. So the committee will meet in room 101 after, we'll do that at 9 o'clock.